scientific ocean drilling ship JOIDES Resolution is drilling into the Sink, a deep reservoir of sediment called the Bengal Fan. The sediment is made of pieces of ground-up rock and debris which have washed into the Bay of Bengal and settled, layer upon layer, over millions of years. These sediments hold important clues about the source, the Himalaya Mountains. The whole system, from the ongoing collision of tectonic plates to the strength of the Asian monsoon, from the deconstruction of the mountains by erosion to the deposition of billions of tons of those mountain bits in the Bay of Bengal. All are linked in ways scientists are trying to unravel.
I'm Yanni Neyman from the Lancaster Environment Centre in Lancaster University, and I research how the Himalayan mountain belt formed. The Himalayas is a type example of continent-continent collision. It's a collision that's going on today. We've still got the mountains rising up today. So if we want to understand processes by which our crust deforms, and that includes earthquakes, which are of importance to the much wider community, then we have to look at this type example and work out what's going on. And the other reason why the Himalayas and Tibet are important is they're thought to have had a major influence on global climate. And so if we want to understand what's affecting the global climate today, we also need to look at the past record and see what changes have happened in the past.
I am Camilo Ponton. I'm a Colombian geologist. I'm currently a researcher at the University of Southern California, and I study climate change. The focus of my study is reconstructing the history of the Indian monsoon. When did the system start, and how has it changed its strength or weakness over time, which has big implications for the amount of rainfall that people see on land, and they sustain their families and their crops based on this rainfall. Today, the Asian monsoon is one of the most active climatic systems on the planet. According to different continental configurations in the past, the atmospheric circulation was different and precipitation patterns on land would have been different. So one of the main objectives is understanding when this started and what's the relationship between the beginning of this atmospheric circulation to the uplift of the Himalaya. The reason we study sediments is because they keep a long-term record of what happened on land. The source of the sediments is erosion by wind or by water that's transported into the bottom of the ocean. And by recovering this sediment core, we're able to travel in time and see what the conditions were on land at particular times. The way we do this is by chemical analysis of this sediment. So properties of this sediment tell us about the environmental condition that this sediment was produced.
Well, I'm Albert Galli. I'm professor of geochemistry working in University of Lorraine in Nancy, France. And I'm interested in isotope geochemistry. Well, the Himalaya is the largest orogen mountain, and therefore, if there is a relationship between the formation of mountains and the change of climate along millions of years, the effect of source to sink for the carbon, then we should be able to see it around the Himalaya more than anywhere else. I've been studying some of the aspects of the sink, namely the ways that the weathering of rock on the continent consume CO2 by the chemical weathering, the formation of soil, and through that process the amount of CO2 in the atmosphere is kept to low level. And if the Himalaya has an impact, we should see less CO2 as soon as the Himalayas start to build up. It's also the sheer amount of sediments that are transported and again eaten away at the bottom of the ocean here, where organic material gets buried. So that's the two parts of the sink and the forcing that the Himalaya can have on the carbon cycle. there is a story building up and we're still collecting the information.